Thanks to all of you who are able to participate in our call today. Before we start, I just want to preface this talk with the caveat that I am human and I am fully capable of making mistakes and misspeaking. So I'd just like to ask you to please take note of anything in this presentation that you might have questions about and just bring it up at the end of the webinar and we can discuss it and resolve any questions that you might have so that we don't go away wondering about things. I would really appreciate that. I'd also like to clarify that even though I represent PMI and we do make ropes here in the United States, this is not a sales presentation. Our focus today is on understanding how ropes are made, how ropes are tested, and how they're used, with our ultimate goal being to know why you prefer what you prefer, how to choose the rope that you need, the right rope that you need for the application that you use it in. This presentation is intended to help you learn about life safety ropes, but it should not be a substitute for appropriate instruction. It's best used as a supplement to hands-on training with a professional trainer. In today's presentation, you'll find out more about how to identify life safety ropes, how to determine what ropes are most appropriate for what type of use. PMI also has similar resources to assist you in learning how to care for, inspect, and store your rope. Remember, selection, care, and maintenance of life safety ropes is a subjective process, and it takes years to become adept. Until then, seek assistance as needed, and always feel free to give the team at PMI a call anytime. Again, our focus today is on figuring out exactly what the test data reveals and understanding what the test data doesn't reveal and what that means to you. There are a couple of different types of criteria that we use to select the equipment that we use. The first is subjective criteria. Subjective criteria kind of has to do with the warm and fuzzies of rope selection. It has to do with brand recognition, whether or not we like the rope, like the color, the name, how it's designed. Sometimes it might have something to do with what kind of beer the sales rep drinks and whether he bought you any at the last trade show you attended. There's a lot of different reasons for selecting different kinds of ropes, and unfortunately, we're not really in control of the subjective criteria nearly as much as we are of the objective criteria. So we're going to focus today on objective criteria. Objective criteria has more to do with things you can measure, specifications, tests, whether or not it meets standards, whether it's compatible with the other equipment that you use, whether your authority having jurisdiction has approved it for your use, is it strong enough, is it the right diameter, that kind of thing. Those are the things we're going to focus on today. We're going to explore some of the details and some of the testing behind that kind of information. There's a lot of reasons that people use ropes for safety. Sometimes we hear the rope, life safety rope, and we think it applies to one specific kind of rope. But as we're going to see today, that's not at all the case. Often when we hear the term life safety rope, recreational pursuits like climbing and mountaineering come to mind. Even these differ from one another, though, and the guy in this picture is definitely going to want a different kind of rope from the guy in this picture. Sport climbing has some specific needs as well. We're not going to talk much about that today, but you can expect this to be a topic of a future webinar. We also aren't going to talk a whole lot about caving, canyoneering, or any of its distant cousins. Instead, our primary focus is going to be on rope for professional use. We're going to talk about ropes for various forms of rope access. We'll talk a little bit about ropes for conventional fall protection. And we'll talk about ropes for rescue, specifically technical rescue, including the difference between mountain rescue applications as compared with urban technical rope rescue, like fire rescue, and how that differs from ropes for emergency escape and other special uses like water rescue. Some of your decisions about which rope to use might be dictated to you by a regulation or operational procedures or maybe by your authority having jurisdiction. Every use that we have has inherent concerns that will also help you settle on objective criteria, like what diameter do I need, what material do I need to use. Most importantly, though, verify compatibility between your ropes and your equipment before you engage in any kind of high-angle work. Hardware, such as descenders or ascenders, are typically designed and built to work best with a specific diameter or maybe even a range of diameters. Your rope has to be compatible with your hardware for your safety. That comes first. There are many different kinds of standards. We're going to start with test methods, which you see the first list here, the Cordage Institute standards listed there are all test methods. They tell exactly how a rope's to be tested. They tell how it's to be terminated at each end for the testing, what kind of conditioning must occur prior to the testing, how fast it must be pulled, things like that. Test methods defined by Cordage Institute also have a few specifications. For example, they tell minimum diameters, minimum breaking strengths in order to be called a life safety rope. But they're only minimums. That's really all they talk about. Whereas NFPA 1983 from the National Fire Protection Association is more focused on use-oriented applications, such as what diameter ropes are appropriate for which kinds of rescue applications. What other considerations do you need to keep in mind when rigging for rescue applications? So it's more focused on selecting the ropes that have been tested according to Cordage Institute standards, selecting which ones are most appropriate for rescue use. Similarly, the UIAA, or Union of International Alpine Associations, refers to low-stretch ropes as a specification. It refers to the test method from Europe, the European norm, EN 1891, and it talks about specifications in terms of or in relationship to those test methods. So there is a difference between test methods and specifications. So first we need to understand how the ropes are tested, and then we need to understand what our own needs are, the specifications. And then finally, we need to understand the relationship between how the numbers are reported and what it is we need. The key objective factors that are measured by most test labs for life safety ropes include strength, diameter, and elongation. There are other things tested, of course, but these are the primary ones that occur and that we pay the most attention to. Static or low-stretch ropes that are intended for life safety applications should be clearly noted as being for a life safety purpose, and they should meet appropriate life safety equipment standards. In the United States, test methods for static and low-stretch ropes are set by the Cordage Institute. Look for ropes tested to Cordage Institute standard CI 1801 or meeting the requirements of use standards such as NFPA 1983, which refers to CI 1801 as a requirement. Cordage Institute is also working on a dynamic rope standard as well as a standard test method for heat resistance for life safety rope. However, these standards aren't finished yet, and so we won't be able to refer to them. In the United States, Cordage Institute provides a reference point for other standards. It provides primarily test methods. It replaces the old federal test method 191, if you're familiar with that. Cordage Institute life safety rope standards are cited by National Fire Protection Association, ANSI Fall Protection, Society of Professional Rope Access Technicians, and other use-oriented organizations in their specifications for life safety ropes. Any rope that is intended to support a live load will clearly be identified as being a life safety rope. Commodity ropes such as clothesline, tie-downs, or hardware store rope should not be used for life safety purposes. That sounds like it really ought to be a foregone conclusion, but believe me, it happens. Be sure that your rope comes from a reputable manufacturer. It should be properly labeled according to its use, and the label should clearly show test results such as the strength, diameter, elongation, things like that, as well as how to reach the manufacturer in case you have additional questions. That said, just because a rope sports a life safety label doesn't mean it's identical to all other life safety ropes. Just as all makes and models of cars are not the same, so it is that ropes have different performance characteristics that you should be aware of. To begin with, let's talk about some different kinds of rope construction, that is, how ropes are made. Laid ropes are three-strand twisted ropes. Typically are not used nearly as much in life safety applications as they were some years ago. Laid ropes offer a certain amount of mechanical elongation that's simply due to the untwisting of the rope when you load it. This also creates a little bit of spin in your system, which can be a little disconcerting. Another thing we need to know about laid ropes is that the fibers are exposed to hazards throughout the length of the rope. Vibration in the system also occurs with laid ropes. You can actually feel or hear throughout the length of the rope when you're running it over an edge or through a system. Another type of rope construction that we don't see much in life safety applications is plated. Plated ropes are fairly softly braided, and because of that, they offer a certain amount of mechanical elongation as well. The soft braid additionally tends to cause the rope to snag on things that may be nearby, and also the fibers are exposed to hazards throughout the length of the rope. Another thing to know about plated rope is that when you tie a knot in it, the bend ratio is very, very tight. We're going to get into that a little bit later. Today we're going to talk primarily about braided ropes. We're going to talk about solid braids, which are, as the term suggests, solid. We're going to talk about hollow braids, which is really a round braid that's braided around a hollow core. We're going to talk about double braids, or braid-on braid. And then we're going to talk about kern mantle ropes. Double braids are actually a type of a kern mantle rope. Kern mantle actually refers to any rope that has a core and a sheath. The kern being the core, the mantle being the sheath. In order to make a kern mantle rope, we actually run a core through the sheath while the sheath is being made, while it's being braided. So the sheath is actually braided around the core of the rope. So you can put pretty much anything inside there for a core. Kern mantle life safety ropes have become quite common in recent years because of the features that they offer. They're very common in life safety applications because the inner core provides the vast majority of the strength, and it's protected throughout the length of the rope by the sheath. So with sheath protecting the core, if anything should damage the rope, such as a falling object damage the rope or what have you, typically it's just the outside protective fibers that are damaged, and the internal load-bearing fibers are kept safer. Kern mantle rope can be made with a variety of properties depending on what fiber you make it out of, as well as how you weave it, how you make it, how you design it. It can have different levels of knotability, tight or not elongation. The elongation can be stretchy or less stretchy. It can be made with different strengths as well as different abrasion resistance, just depending on how it's designed and what materials it's made out of. Life safety rope is usually referred to in terms of elongation. This is how we differentiate between the different kinds of kern mantle ropes that are out there. Three common types of kern mantle life safety rope are dynamic, which is on the left, the purple one, low stretch, the white in the middle, and static, the red on the right. These terms are not meant to be anything other than descriptions by which the ropes are typed or categorized, but it's a good way to use to categorize them. Cordage, small diameter stuff, is in a category all its own, and it should not be considered the same as life safety rope because it's not intended to be a sole support line. For more information about the selection of dynamic rope, look for an upcoming PMI webinar on selection of dynamic climbing rope. But for today, we're going to focus on low stretch and static ropes. The line between low stretch and static is relatively fine, but it's important to distinguish between the two when it comes to practical application. For example, a low stretch rope might be preferable for belaying heavy loads, while a static rope is more stable for lowering and raising. Kern mantle, dynamic rope, tends to be a high twist core rope. It tends to have a lot of elongation. It's made for catching a heavy falling load. So the twist in the core, as well as heat treatment helps to lend to that force absorption capability. It has relatively less percentage of sheath as compared with a static or low stretch rope. Low stretch and static ropes are intended for raising, lowering, ascending, and descending. They're not really intended for lead climbing or for significant lead climbing falls, although it's fine to take shorter falls on them, such as in a top rope belay. Low stretch and static kern mantle ropes are frequently used for belaying rescue loads as well as for catching short falls. Low stretch rope is sometimes called Eurostatic or semi-static rope. In Europe, what we call low stretch rope is often interchangeably referred to as static. Low stretch rope has, according to the Cordage Institute CI 1801 standard, greater than 6% but less than 10% elongation at 10% of its minimum breaking strength. Static rope isn't really addressed by European standards. It has a relatively straight core and less than 6% elongation at 10% of its minimum breaking strength. In Europe, they don't use this type of rope, and it became very confusing for a period of time because what we've referred to as static rope in the United States and what Europeans referred to as static ropes in Europe were quite different beasts from one another. The Cordage Institute standard, CI 1801, has helped to clarify some of that, and what we refer to as the low stretch rope is actually quite consistent with what the European norms specify for low stretch rope. I want to point out just the difference in construction and how that affects the elongation of a rope. Remember the plated rope that we saw earlier? That plated rope is actually one of the stretchiest ropes out there just due to its construction. Laid rope is also very stretchy, and static kern mantle rope is the least stretchy of all. Dynamic rope is also kern mantle, but it's designed in order to be stretchy, so it has certain characteristics that are built into it to make it stretchy so that it can catch the impact and reduce the impact of a falling load. I also want to point out the effect that construction has on rope strengths. For a given diameter of rope, relative strengths will differ just because of the construction. As you can see here, the kern mantle construction is one of the stronger constructions out there, while things like plated and laid ropes of a similar diameter will be less strong. Again, dynamic rope, which has other features built into it to make it elongate more, is also less strong. Again, we're going to focus primarily on low stretch and static kern mantle rope. As you can see, the rope on the left, we call that low stretch rope. It has a fairly thick sheath. It has a certain amount of twist in the core, and it's designed in order to have 6 to 10% elongation at 10% of its minimum breaking strength, making it a little bit stretchy, but not very stretchy. Static rope, on the other hand, is made to have absolute minimal elongation. The core fibers tend to be very, very straight. The sheath tends to be very, very thick, and it tends to be designed in such a manner that it is very, very stable for lowering or raising or hauling. You can see here, I want to point out the little tag that you see sticking out of the tops of both ropes. According to the Cordage Institute standards, all life safety ropes that are made in the United States are required to have a tag like this running through the core of the rope with information repeated every couple of feet pertaining to when the rope was made and who made the rope. So if ever you have a question about who made your rope, what kind of rope it is, or how old it is, you can always just chop off the end and pull this little tape out. It's buried somewhere in the core fibers. Diameter of ropes is measured with calipers. It's measured in multiple locations with a constant force on the end of the rope to make the rope straight. The elongation is calculated as The diameter is calculated as the average of 12 measurements throughout a certain distance. The Cordage Institute standard actually specifies how far apart those measurements have to be, and that they have to be in different, they have to be measured kind of in different radiuses. So it's a good way to tell that your rope is very consistent. The other thing is that if the standard deviation of those measurements varies by more than 5% throughout the 12 measurements, it disqualifies the rope from actually passing the test. So that helps to ensure that you have a very consistent diameter in your life safety ropes. The other thing I want to point out is that the diameter reported is required to be within 5% of the actual diameter. Why do we say that? Well, it's because if we measure a rope at 11.1, or if the measurements come out as 11.1 millimeters, people aren't going to like that because we're used to dealing in half millimeters, 11 millimeter, 11.5 millimeter, 12 millimeter, 12.5 millimeter. So if it measures out at 11.1 or 11.2, typically we'll report those numbers as the closest nearest half millimeter, just because that's what we're most familiar with working with as end users in the field. So it's just to help not confuse things. I also want to point out that the EN 1891 is the European standard, and it addresses ropes from 8.5 millimeters to 16 millimeters. You'll notice that that differs from the Cordage Institute standard. The Cordage Institute acknowledges ropes all the way down to 7 millimeters. That's because in the United States, we tend to use 7 millimeter ropes quite frequently in emergency escape, and we still consider those to be ropes. So we address ropes all the way down to 7 millimeters, whereas EN 1891 starts at 8.5. The other thing to note here is that the EN 1891 does have a type A and a type B of rope. They don't so much separate by diameter, they just separate by type A and type B. Type A meets their minimum basic requirements, and type B doesn't meet the normal requirements. So whenever you're buying an EN 1891, you need to be aware that that rope might have different characteristics depending on whether it's a type A or a type B. Breaking strength is probably the thing that we talk about the most when it comes to rope. This is important because it kind of provides the foundation of our system. But I do want to let you know that if you're familiar with the old Federal Test Method 191A or some of the other non-life safety rope standards out there, some of the commodity rope standards, don't actually measure breaking strength in the same exact way that life safety rope standards do. Life safety rope standards measure breaking strength and diameter and pretty much everything else as being very, very accurate. The breaking strength of certain commodity ropes and of the old Federal Test Method 191 was more oriented on what they called a nominal strength. A nominal strength was focused on the diameter. It measured the diameter of the rope, and it weighed the rope, and it assumed that a rope of a certain diameter and a certain weight would be a certain strength. We don't do that in the life safety rope standards. We tend to measure more specifically. In fact, we use something called 3 standard deviations, or the 3 sigma method. In this method, breaking strength is typically measured by pulling several samples to failure, averaging the number, and then subtracting 3 standard deviations from the mean of those measurements to come up with a 99.9% confidence. It's kind of a statistical way to be able to tell that your rope is actually going to break at something higher than the rated breaking strength of the rope 99.9% of the time. So it's important to know that it's not an average breaking strength. It's not a highest breaking strength of a series of numbers. It's not our favorite number out of the number of tests that we did. It's actually 3 standard deviations below the mean. The Cordage Institute specifies minimum breaking strengths for various diameters of low stretch and static life safety ropes. Most ropes from reputable manufacturers will actually test higher than these figures, but the only way to know for sure is to ask for a third-party certification. As you can see, there's minimum requirements for different common diameters. A 7 millimeter diameter rope must be at least 2,200 pounds. An 8 millimeter must be 2,875. A 10 millimeter must be at least 4,500. The most common ropes that we use are probably the 11 millimeter at 6,000 pounds or greater, and the 12.5 millimeter at 9,000 pounds or greater. You'll also note on the left-hand side column an inch reference using English units. So you can see the correlation between millimeters and inches. So that's an important thing to notice, that these are not precise. Actually, half inch actually comes out to 12.7 or so. So it's not exactly precise on the scientific measurements, but it's what we tend to call things in the industry, and so we've drawn some correlations there as well. I'd also like to point out the difference of breaking strengths in different diameters of ropes. As you can see, naturally, the fatter a rope is, the greater diameter it has, the stronger it will be. So how do you know what strength of rope is best for you? Sometimes this information will be dictated by the company or agency or the authority under having jurisdiction that you're working under. But if this isn't the case in your situation, you might be tempted to select a design load factor as a starting point. That is, how much load do you expect to put on the rope, and how much stronger than that do you want your rope to be? Keep in mind, though, that the component design factor is not the same thing as a safety factor. So design factors come in, design factors that are common in life safety applications range from 2.1 to 15 to 1. So this means that the item would be 2 times to 15 times stronger than the load you expect to put on it. In the case of rope, you can expect a 20 to 30% decrease in strength when you introduce a knot. There are other decreases in strength that occur based on other elements of the system. So how much the design factor matters as compared to the overall system is somewhat negligible. I would prefer that you actually think of your systems in terms of system safety factors. This is much more important. That is, what effect do the various components have on one another, and how strong is your system as a whole once it is completely rigged? It is possible to make a 12.5 millimeter rope system that is less strong than an 11 millimeter rope system, depending on how you rig it. So it has to do with the system and how all the components interact together. This is something of a subjective analysis because it depends on your specific application and use, and it has to be calculated using a combination of education and experience and data. So obviously it takes a lot into consideration and should only be calculated by experienced rope technicians. But when selecting your rope for use, pay more attention to your system safety factor than you do your component design factor. Your safety factor is your weak point in your system divided by your anticipated load. Elongation is a consideration that's often ignored when selecting between static and low stretch rope. This variable can make a great deal of difference, and so I'd like to pay a little attention to it now. As we talked about before, a static rope can have up to 6% elongation at 10% of its minimum breaking strength, while a low stretch rope might have up to 10% elongation at 10% of its minimum breaking strength. The difference between 6 and 10% when you have 100 feet of rope out could mean several extra feet of rope stretch. That distance may be useful in terms of absorbing forces, but it could be deadly when it comes to precise and accurate positioning of a load, or if you're loading a patient mid-face and the weight of the load changes, or if you want to reduce the amount of travel during an unplanned shock load. On the other hand, the more static a rope is, the less forgiving it will be in terms of absorbing shock loads. So the take-home message here is that one is not necessarily better than the other. It depends on your specific use, your application, how you're putting it all together. Only you can analyze the unique configuration and needs of your system and select the rope and equipment that's most appropriate for your use. The topic of impact forces often comes up when we talk about static ropes and using static ropes to catch a fall. Keep in mind that static and low stretch ropes are fine to catch a fall that is a factor 0.3 or less. So a 0.3 fall factor is equivalent to dropping a load 1 foot on 3 feet of rope. So a 0.3 fall factor is fine on a static or low stretch rope. You can drop a load 1 foot on 3 feet of rope, or the equivalent multiplied out on a static or dynamic rope, static or low stretch rope. A dynamic rope is more appropriate for lead climbing falls, or falls where you might actually be above your anchor. This is tested in this configuration here. When we test dynamic ropes, we actually anchor the rope to a test weight, and that test weight is about 180 pounds. We then run the rope through an edge to simulate a carabiner and then tie it off behind that edge. The rope typically breaks at the edge. So when the rope is tied off, we drop this system down. We drop that weight down so that it ends up down here and it impacts the rope, and that rope has to reduce the impact force of the fall to 12 kilonewtons or less. So it's about a factor 2 fall. It's a factor 1.8 fall, so it's a lot higher, and it has to reduce the force of that falling mass to 12 kilonewtons or less. So that's why dynamic ropes are better for use in lead climbing falls, but static ropes can be used in lesser falls without any problem. I want to point that out because the elongation does matter when we're trying to position a load and when we're concerned about bounce in our system. You can imagine these ropes that are down in the stretchier end of the curve, like the yellow or the blue, those have a lot more elongation, and your system is going to be a lot more stretchy, which will translate to less control in moving lowering or raising a load. Another thing we think about a lot with life safety ropes is heat resistance. Typically, this topic comes up when we talk about emergency escape for firefighters. There isn't really an official rope test method yet for the heat resistance of a rope, but the nylon, polyester, aramid, the fiber manufacturers do publish high-temperature working limits for those fibers. I want you to notice here that the nylon high-temperature working limit is about 250 degrees. That's about 25 degrees lower than polyester, and aramid is about 100 degrees higher than nylon. Polypropylenes and Spectra, Dyneema, high modulus polyethylenes really shouldn't be used in high heat environments. But when it comes to nylons, polyesters, and aramids, there really isn't enough difference to shake a stick at, especially when you take into consideration the time and temperature curves that occur in a fire. A fire gets really, really hot really fast and exceeds 200 to 400 degrees pretty quickly. So keep that in mind when you're selecting a rope, that maybe having that Kevlar rope might not necessarily be as important as having a rope that catches a fall or absorbs force or has a lower impact rating. Knotability is also a topic that I'd like to discuss. Knotability is a feature that's measured by most standards, and there is a minimum requirement in those standards to ensure that you don't end up with an entirely stiff rope. But most of us don't really think about it consciously, and we certainly don't specify it usually. Sometimes we subconsciously like the feel, referred to as the hand of a rope. A rope with a softer hand or greater knotability is usually preferred from an aesthetic point of view. However, there are some downsides to that softer hand. One of the downsides is that the easier it is to snug a knot up in a rope, the more difficult it is to untie that knot after you've put a heavy force on it. People worry about the strength of knots in a rope, and with good reason. In general, the tighter the bend in a rope, the more the strength is compromised. Strength reduction as a result of knots in nylon and polyester life safety rope begins to be significant at less than about 1 time the radius of the rope itself. So when the bend becomes tighter than the rope, then it begins to be significant. Therefore, knots with straighter lines and gentler bends are best. Now, this isn't necessarily true with aramids, HMPs, and other high-performance ropes. With these ropes, be really cautious. These fibers respond very, very differently, as we'll see in a minute, and usually less favorably to knots. So, looking at this particular knot comparison, you can see that the different knots actually retain strength at different rates. And if you think about the knots and how the knots are made, you can draw a correlation between the straightness of the rope, or the straightness of the width of the bends in the knot as compared with the retained breaking strength. Something else that people seem to not be quite as familiar with is the effect of the sheath design on abrasion resistance characteristics of a rope. Again, there's not yet a universally agreed on test for this characteristic because the most consistent test methods don't necessarily correspond with the way that we really use ropes. In short, though, you can generally assume that the rope with the greater abrasion resistance will also have the lower knotability. In other words, typically tighter, stiffer ropes have greater abrasion resistance. In the picture here, I want to point out on the rope on the right, that wasn't really abraded over an edge. It was actually a result of a rock getting caught inside a gree-gree, and that did what you see to the rope. The rock got caught inside of the descender next to the cam, or between the cam and the rope, and so the belayer didn't see it, and you can see what happened. So the tighter the weave, the stiffer the rope, the more abrasion resistance you're going to have. One clue that you can use to determine abrasion resistance has to do with the number of bundles of yarn that a rope sheath has. Remember that a rope making machine we talked about, remember that rope making machine that we saw earlier on the slide? We didn't actually talk about it a whole lot, but the number of yarn bundles that are used in the weaving of that sheath is actually an important factor in abrasion resistance. Sometimes you hear this called carriers. A 16 carrier rope uses 16 bundles of rope to go around the core. PMI Classic is a 16 carrier rope, and you can see in the diagram on the left that it actually uses fewer bundles, but they're all thicker, whereas the picture in the middle is of a 32 carrier rope. this is a PMI isostatic or Access Pro or both like this. These use a higher number of bundles, but each contains less yarn. A 48 carrier rope, such as a dynamic climbing rope, has even more bundles that are even less thick. So the net result is the fewer the number of carriers, the thicker the sheath, and vice versa. The flip side of this is that the rope with greater abrasion resistance, the rope with a fewer number of carriers, is also going to have the lower knotability. It's going to be stiffer. Everything is a balance, and gaining one thing usually means compromising something else. Another thing that's affected by knotability is how much a bend affects the rope. Of course, this is affected by a lot more than just bend ratios, but we do need to think about what happens to a rope just during general use. For example, just bending over carabiner edges or whatever. The life safety rope community became most aware of this problem when aramids first became popular for life safety, because aramids are short, brittle fibers that are kind of like fiberglass. A series of testing that was done in 1992 actually highlighted this problem. As you can see in the bottom set of testing, 8mm cord that was a combination Spectra Kevlar was tested. There were 6 samples in this particular group of tests, and you can see where there was a 160-degree bend over a carabiner edge in the picture on the right. A 200-pound weight was hung from that as though to simulate a human, and it was run back and forth 250 cycles, just a couple of inches, back and forth, back and forth, back and forth across the carabiner, as you might do over a period of months or weeks or years of use. With the Spectra Kevlar blend rope, there was over 50% of the strength was lost during these tests. Similar tests were done by Tom Moyer and Chris Harmston in about the year 2000. In these tests, very similar cord 7mm Spectra Kevlar blends were bent 180 degrees, this time over a 90-degree steel edge, so it was a little bit of a sharper edge, but it was only a 40-pound weight. They ran 200 cycles across this, and again, the rope lost about 50% of its strength. So the take-home message is that the Spectra Kevlar blend, and I can tell you from experience that the culprit was the Kevlar here, the Kevlar rope actually, just through repeated bending abuse, will lose a certain amount of its strength. In fact, a good bit of its strength. What does this mean to the ropes that we use every day? Similar tests performed on other types of ropes had varying results depending on the fiber. As you can see, nylon is pretty resistant at about 9.4% strength loss under similar tests. Again, Kevlar was about 53% strength loss. Kevlar Spectra blend was about 54% strength loss. Spectra tests alone, just the Spectra, that test was pretty inconclusive, and that's due to the fact that Spectra is a very slippery fiber. Spectra does not hold a knot particularly well, so when you tie a knot in it, it will untie itself when you pull it under tension. This is the reason the slipperiness of Spectra, the low abrasion resistance of Spectra, is the reason that Spectra is often encased in a nylon or polyester or other sheath. But even in this case, if you tie a knot in the Spectra core will simply pull itself through the sheath, and you'll be left with a tied sheath and a piece of Spectra coming out the other end. So as we can see, they're not very predictable, and some of the newer, fancier fibers that have very, very high strength actually have some real significant problems when it comes to bending or even knot tying. As with some of the other things we've mentioned today, there's not presently a test for this in the Cordage Institute. There's not one in National Fire Protection Association. There's not one in ANSI. There's not even one in the Euronorm standards. This is just something you need to be aware of, and if necessary, run your own backyard tests to ensure that you're going to be safe in the systems that you use. Another thing I want to talk about is a rope's reaction to water. When it comes to specific uses in water, floatability often comes up in relation to water rescue. Floatability has to do specifically with what we call specific gravity, how heavy the rope is. The nylon has a specific gravity greater than 1. Anything with a specific gravity of greater than 1 is going to sink. Anything with a specific gravity less than 1 is going to float. So you can see here, nylon doesn't float, polyester doesn't float, aramid doesn't float. However, polypropylene and high modulus polyethylenes do float. That said, there are certain kinds of coatings that you can put on to ropes that will help their floatability. It doesn't make their specific gravity any less, but it makes them absorb water less. So nylon, which does absorb water, can be treated with a surface treatment that will make it absorb less water and make it float better. It doesn't make it float great because it's still heavier than water. So these are just something, again, to be aware of, and not something that there's a really good test for. And if it's important to you, you may want to devise your own backyard test to test for it. But since we got to the subject, let's talk about fibers just a little bit. We need to talk about all of the fibers, and we'll start kind of with big groupings like natural fibers and man-made fibers. Steve Hudson likes to say that this picture shows two different types of rope plants. On the top, there's a natural fiber rope plant, and on the bottom, there's a man-made fiber rope plant. Natural fibers, such as manila, sisal, cotton, that kind of thing, those shouldn't really be used for life safety applications. Although they do strengthen while they're wet, and they're very easy to make and pretty cheap, they have a very low strength to weight ratio, and their lack of continuous fibers do make them a little susceptible to everything from abrasion resistance to low strength. So unless you need something that is highly digestible by livestock, which I'm sure is very important to most of you, you really need to stay away from these kinds of fibers. Most of the life safety ropes that you see are made of either nylon or polyester. Nylon ropes are historically, most recently, made of nylon because nylon is very, very strong, but it still has a high elongation characteristic, and that makes it very forgiving when we do fall. So note that the high temperature working limit of nylon rope is pretty high, 250 degrees. Your rope isn't going to fall apart or break at the 250-degree temperature, but the performance of the nylon is going to deteriorate to the degree that the rope really should be discarded once you get off of it. Unlike some of the trendy high modulus fibers that we'll talk about in a moment, nylon is very abrasion resistant. It's also stronger than polyester, and it absorbs energy pretty well. While nylon does lose up to 15% of its strength when wet, the strength is regained when the material dries. Nylon's a pretty good choice for rope. Polyester is also a pretty good choice for rope. These have recently come into vogue in the life safety rope realm, at least partially due probably to the low cost of polyester by comparison to nylon. Note, however, that polyester as a fiber does have only about half of the inherent elongation that nylon does. Other characteristics, including strength and heat resistance, are relatively comparable to that of nylon. Some rope users select polyester for its chemical resistance, but even though polyester is more resistant to acids under a high-intensity exposure, nylon is more resistant to alkalis. So keep that in mind. In either case, the rope has to be exposed to incredibly high concentrations for very long periods of time, or it has to be exposed to intense heat at the same time of the chemical exposure in order for the deterioration of the fiber to be very significant. In fact, the exposure limits that would destroy the integrity of a life safety rope are so intense that the user using the rope wouldn't be very happy either. That said, any rope that is subjected to any significant chemical contamination should be retired as soon as possible. Things to be particularly careful of with polyester rope are its lower dynamic energy absorption and the fact that it's more slippery to repel, lower, or belay on than with nylon. Polypropylenes are seldom used in life safety applications, with the exception of water ropes. Polypropylenes have a very low breaking tenacity by comparison to nylons and polyesters, but they do float. They're very stretchy, so they have a pretty good shock absorption capability, but they have a very low high-temperature working limit. So the poor abrasion resistance, the poor UV resistance, and the low strength make polypropylene a pretty poor choice for life safety applications where your life really is hanging in the balance. Aramids, which we talked about earlier, do have some advantages in strength. They're very, very strong. 18 to 26.5 grams per denier is pretty strong. It's 2 to 3 times as strong as nylons or even polyesters. But it has very little elongation at break. That means that aramids, if you fall on them, are very unforgiving. It means that when you fall on an aramid rope, that force is transmitted not only to your body, but also to the anchors. There's also that self-destructive action that we talked about earlier, and that can be a pretty important factor in ropes that you're actually using. Another newer fiber that we are seeing used more and more is called ultra-high modulus polyethylene. It's also sometimes called high molecular weight polyethylene. These fibers are not the same as aramids, although sometimes the two get confused with one another, and sometimes they're even blended together in the same rope. We know these ropes best by their trade names, Spectra and Dyneema. These are very, very, very strong ropes, up to 30 to 35 grams per denier, which is way stronger than anything we've talked about before. Not to mention, they float, which makes them great for water rescue applications. However, again, there's very little elongation at break in these ropes, so you have to be very, very careful when using these ropes because they transmit the force of a fall or of a load directly to the anchor and directly to the user without absorbing any of the force within the rope. They also have a very low high-temperature working limit, and as I mentioned earlier, they're very slippery and don't hold knots very well at all. So now that we know how the ropes are tested and what all those numbers mean, it's maybe more critical now to explore what that means to you. Which ropes are the most appropriate for your specific application, and why? As you might imagine, I'm going to throw a good bit of the answer back on you to decide, because only you can know how your system behaves, what kind of performance you expect, what features and factors are most important to you, and what other gear you need to be compatible with. However, let's go ahead and walk through a few specific applications and at least think about some of the things you should be thinking about. We didn't really talk about dynamic rope, and I'm going to go ahead and make sure that we know that that's off the table before we start. You can expect to see a deeper discussion of dynamic climbing ropes in a future PMI webinar, but for now, suffice to say that only UIAA or similarly certified ropes should be used for lead climbing, where the climber is likely to be above his anchor or where he's a significant distance out from his last piece of protection. Mountaineering is a different beast from sport climbing, though, and for mountaineering, there are times and places where static or low-stretch ropes might be appropriate. For example, for fixed lines for ascending, top roping, and other places where durability is more important and where fall factors are low, static and low-stretch ropes are a great choice. Many mountaineers use static and low-stretch ropes for glacier travel, since fall factors there tend to be low, and dynamic ropes are not fun to use in the haul systems that you might use when you're pulling somebody out of a crevasse. In wet conditions like glaciers, dry static ropes are worth considering as well. A rope that's dragged over snow or ice will become wet, which makes it heavier and will also affect its performance a bit. Recreational caving is another place where static ropes are a good choice. In caves, lead climbing is less common than rappelling and ascending. Because static ropes don't stretch very much, they offer more stable rappels. This allows the rappeller more control over his or her position. Using ascenders to climb up a rope is also more efficient on a static rope because there's not as much bounce. Bounce in ascending makes the climber less efficient and requires more energy. Bounce can also increase the rope's susceptibility to abrasion at the anchor or over an edge. These are all good reasons to use static rope, not low stretch, static, in caving. Because both strength and weight are a consideration, you usually find 10 to 11 millimeter ropes being used for caving. However, some cavers may use smaller ropes, like 9 millimeters. At 4,500 pound strength, you can still get a good safety ratio out of 9 mil, and they are lighter to carry. Hydrophobic ropes, or ropes that have the dry treatment, are also worth considering for wet caves. Remember, a wet nylon rope is less strong than a dry one, and is heavier to carry. Those who use ropes for canyoneering should keep the same kinds of things in mind because the rappelling and ascending kinds of situations are quite similar. But since this presentation is about ropes for professional use, I'm going to leave the recreational stuff at that, except to say that the same considerations should apply for those who rescue people who are in those recreational environments. Where lead climbing is required to access a patient or to get into a location to rig from, always use dynamic rope for lead climbing. However, when it comes to lowering and raising loads, static rope becomes extremely important, especially in rescue situations where we have multiple people on the line. The static ropes can be very convenient. Lowering a heavy load such as a patient, litter attendants, and other equipment creates a good amount of stretch in the system. The more static the rope, the greater control you'll have. It'll reduce the bounce, and it helps the load not creep when it's in a stopped position. The same holds true for raising. Haul systems are much less efficient when there's a lot of bounce or when you have to pull a lot of stretch out of the rope with every pull. Here again, a static rope is going to increase your efficiency and it's going to improve your system performance. Depending on the environment that you're working in, abrasion resistance might also be a factor. While knotability is important, it might be worth the trade-off of having to work a little harder to tie your knots in order to have a more abrasion-resistant rope and to be able to untie those knots after you're finished. Rope access applications are another place where positioning is important. However, many rope access technicians actually prefer low-stretch rope over static due to the forgiveness that having more elongation introduces into the system. Even though low-stretch rope does allow more bounce and isn't always as abrasion-resistant, we can get away with it here due to the fact that we're generally dealing with lighter loads than in rescue, and we're generally working in a more controlled environment. Usually we see somewhere between 10 and 11 mil rope used for rope access. The 6,000-pound strength offers plenty of safety margin even when we end up doing a partner rescue. Ironically, many of the ropes commonly used in conventional fall protection are not ropes that meet the life safety rope standards that we've mentioned previously. Historically, these tend to be laid ropes, often polyester, and of a 5/8 inch diameter. In the old days, it took a 5/8 inch rope to get up to OSHA's 5,000-pound strength requirement, so that was part of the deal there. Nowadays, with modern technology, 11 mil and 1/2 inch ropes are becoming more familiar. The important thing here is to ensure that the rope grabs you're using with the rope really are compatible both with the diameter and with the construction of the rope. Ropes that are made for laid ropes don't perform the same on kernmantle and vice versa. An 11 mil rope will give you the 5,000 pounds that you need easily. As mentioned earlier, water rescuers have some unique needs. This is the only place you'll see polypropylene ropes still commonly used. Remember, polypropylene isn't as strong nor as resistant to UV as other ropes, but it does float. So this is a good rope for throw lines. Ultra-high modulus polyethylene, or Spectra, which is a polyethylene base just like polypropylene, is also a good choice, and it's much stronger. It's also about 10 times the cost of polypropylene. Bear in mind, if you're choosing high modulus polyethylene rope here, these ropes do not hold knots well, and they have almost no elongation, so be very careful. Some of the forces you can encounter in water, especially swift water, can be extreme. Throw ropes tend to range from about 7 millimeters on up to about 10 millimeters or so. Those who choose 10 millimeters typically do so for gripability reasons, but the reality is 3 millimeters isn't going to buy you much grip on a wet rope. There's other ways to overcome this. For near water use, not in water use, but near water use, where floatability isn't as important, like a high line across a river, your standard nylon or polyester life safety rope is a much better choice than either of these. Another specialized environment is fire rescue, and the thing that leaps into people's minds when you say fire is heat. Remember, though, the high temperature working limit of aramids is still only about 350 degrees. Nothing is fireproof. You have to balance the concern that you have about heat with other concerns regarding the effect of repeated bending, as well as the fact that aramids have so little force absorption capability, which is important for a firefighter who's leaping out the window of a burning building and for his anchors. Most fire rescue situations where rope is used doesn't involve fire at all. When it comes to rescue, it usually occurs in a more stable environment, usually without flames. For this kind of rescue, again, a standard nylon or polyester life safety rope is quite appropriate. The amount of stretch that is preferred usually depends on the technical capability of the team and how forgiving they need the rope to be. Diameter also depends on experience and capability of the team. For teams who don't do as much training, or who might be more likely to overload their systems, or for teams who use very heavy rescue loads, a 9,000-pound or 1/2 inch rope is a good choice. For more highly trained rescue technicians, an 11 mil rope at 6,000 pounds or more is quite sufficient. Clearly, the biggest variable in any life safety system involving rope is the human factor. Typically, when there's a problem, it boils down to not using the right gear, lack of proper training, poor judgment, lack of experience, or worst of all, ego. All of these can be summed up by the fact that we are all human. It takes time and experience to choose the correct equipment and to make the right choices when using it. I really appreciate you taking the time to listen in today, and I'd be happy to entertain whatever questions you might have. If If there's anything that I haven't covered, or that I haven't stated very clearly, or anything that doesn't make sense, by all means, feel free to enter a question in the chat box or contact me by email or phone anytime. I'll be happy to discuss this or other related topics in greater detail with you. I'm now going to turn this back over to Jessica, and she'll drive the boat from here. Again, I just want to thank you guys for attending. Appreciate your attendance, your time, and hope that this has been of some use to you.
Thank you very much, Loui. And let me go ahead and switch screens here. And if you have any questions, go ahead and type them in the chat/questions area of your control panel. And we will take care of those questions for you. It doesn't look like anybody has any questions at the moment, so I'm going to give you a little bit of time to type those in if you do have them. While you're doing that, I'm going to go over a few closing details. You can visit the website shown at the top of your screen to ask Loui further questions. There's going to be a link to email her. You can also see her direct email is shown on the screen. The slides from the presentation are going to be available for download at that link at the website. And also the live recording of this webinar is going to be available to watch. And the PMI webinar series hosts webinars frequently, so you can keep an eye on our website for dates and topics. Our next one should be around the beginning of September. And for news and updates, you can sign up for PMI's e-news through our website shown. You can also follow us on Twitter and Facebook. There we post all of our webinars as well as events that we're going to and just other news and information. And it looks like we have one question. Are red ropes stronger than yellow ropes?
In general, no, there's really not a lot of strength difference between different fibers. You might see some strength differences, some elongation difference even, between colored ropes and white ropes, but between different colors, we don't tend to see any significant differences. And in fact, even the white isn't a significant difference, other than, it's not statistically different.
Okay. And can you recycle ropes?
Absolutely. That's a really good question, and I'm glad you asked it. We do have a recycling program both at PMI West and at our main headquarters. If you want to send your ropes back to us or drop your ropes off with us, we can recycle those and send them off to a good cause.
And you can find more information about our recycling program on our website. If you just go to our homepage at pmirope.com, there is a link to it if you scroll down to the bottom. And that looks like those are the only questions so far. So if you have any other questions, you can definitely email Loui through her direct email shown on the screen, or you can use the link that will be found on our website. And we really appreciate you guys attending. We hope that it was helpful, and thank you, Loui, for doing this. Oh, wait, we got one more question. Let's see. There was a climbing accident somewhat related to the ascender interaction with rope sheath. The climber popped the sheath, slid down the rope, and then the core failed. Is there any research into better understanding of sheath and core?
Actually, there's a lot of research. That's kind of a constant topic of research in our own factory as well as all over. The problem is it can't really be quantified in a very consistent way. There's varying relationships between sheath and core that depend on everything from construction of the sheath, construction of the core, the fibers used. There's just so many variables. The bottom line with that case, though, was don't fall on an ascender. Really bad idea to use an ascender in a position where you can get more than a foot or so of impact.
Okay. Great. Well, I think that is the last question now. So if you have any more that we don't get to or that you don't have time to type in, okay, there's one more, sorry. Can I use a Sharpie to mark the middle of my rope?
That's a really good question. There are there are some Sharpies that you can use. The problem with Sharpies or any other pen is not the ink, but it's the solvent that's used to dissolve the ink and to keep the ink liquid. So some of the solvents are not bad for ropes, and some of the solvents are very, very bad for ropes. To be really sure that you're using a pen with the right solvent or with a solvent that won't damage your nylon, if you just use the Sharpie TEC marker, and the TEC is a trace element control marker. It's made for the aerospace industry, and that's a really good choice for marking ropes.
Okay, great. All right, I'm going to give anybody just a little bit more time to type any in, since we seem to have a couple of people that want to get some in there. Okay, we're going to call that the end, and if you have any more questions, please email Loui. And again, thank you guys for attending, and thank you, Loui, for doing this.
Thank y'all. See you later.
Have a great day, everybody.